exam 2 review session. I just now finished writing the test, so as soon as I do that, I come film this review, and I do that because I'm telling you the same thing I told you last time, which is that I am going to give a bunch of answers away. The difference between the first test and this test is that now, hopefully, you believe me. If you go look at, well, you know what was on the first test. If you go look at the review session, you may notice many times I explicitly stated answers. So, but based on the scores, I think you just didn't believe me that I was actually going to do that, but I did. So I am doing that again, and I know I'm doing that again because, again, I just finished the test. Let's see, other little bits. Some people have asked, is the test comprehensive? Formally, no, because you're not going to be asked about velocity of a gas or light bulbs. However, in some ways it kind of is, because a wave function squared is a probability distribution, that's Maxwell-Boltzmann, and everything's a sine or a cosine wave, and that's like Planck. So we are going to be starting with uncertainty principle, so I will be explicit where the exam starts in terms of the course material, but in many ways it's effectively comprehensive. But again, there are no Maxwell-Boltzmann or Planck questions directly. The third exam was going to be unique. When we get to the next set of material, there's not going to be much quantum mechanics at all. There's going to be some spectroscopy and some kinetics, and so that one will truly be different, and then the final is comprehensive. Last thing is the exam. It is set up the exact same way. It will look the same, it will feel the same, because I wrote it all. Again, this is, I know I hark on this, but I'm telling this for you to be comfortable with it. It should at this point have a very familiar look and feel. You've done a ton of homeworks, you've had a test, you should do better, right? You're getting used to this. So even if you don't think like, well, I don't know that I know anymore, that should be enough. The fact that you're familiar with these things, that should be enough for you to do better. And the more you think that, the more likely it will actually be true. And also, so same format as well, you know, like, I forgot how many, like 5 what's wrong, I think it's 5, I don't quite remember. Anyway, the same number of what's wrong questions, short answer, and then derivation. Of course, if I know this is incredibly hard to do derivations on a computer, so that's why, you know, normally without COVID, I would want to see your work. In this case, I know it's incredibly difficult to type things out on the computer, so I'm going to accept just your answer. You know, you have your scrap paper, have scrap paper, that's fine. Have your cheat sheet. You know, trust the cheat sheet, because again, I wrote them all. Every time I write a question that needs a cheat sheet equation, I make sure it's on the cheat sheet. I put them together at the same time. So you know, just you can work it out and put the answer. But let me offer this advice. If you're at the end of the test and you have some spare time, why don't you add whatever details you can to the derivation to help get some extra credit. That's one thing you folks could have done last test to have helped a little bit, help yourself, is trying to give me a little bit more to work with. Be careful with that on the other questions, though, because you can go too far. Now, of course, where does it balance out? I don't know, but what this, you know, ABC, right? That's how it balances out. Let's see. Again, I am going to tell you exactly where we're going to start. I'm probably going to go long. I may go way long. I don't think I'll be short. I may be long for this review. Not to, you know, I'm supposed to keep it down to an hour, 50 minutes, but I'm not even wearing a watch. I'm just going to cover what needs to be covered. So if I'm long, I hope you don't, please don't file complaints with the authorities, okay? Because I'm doing that to try to help. I actually have a grant to write. So anyway, all right, so the exam does begin with the uncertainty principle. So we kind of cut that subject right in the middle with the last test. We started it, but we didn't finish it when test 1 came along. So it will be a part of test 2, especially that bit about waves, how little particle in the box can be thought of as a sum of like momentum waves. Anyway, I'm getting ahead of myself. So again, we're going to start with uncertainty, and this is on the test, by the way. Not that I'm going to say, hey, write this down. I mean, that's stupid. That's like in kindergarten when you write down the alphabet, like I still remember they gave us the alphabet and they said just write over it. And you got points. And I remember thinking that was kind of stupid. But remember that these are standard deviation, variances. A standard deviation squared is technically a variance. Statistics, right? I think a lot of you, maybe you didn't have statistics as a formal math class. I think I was not required to have it. I think I've just had enough classes that talked about statistics that I know something about it. I remember, all I remember is standard deviation is like the error bar on your graphs, and variances are the square. And variances are kind of important because that's where the formulas come from. You always get formulas for variance, and the standard deviation is the square root of that. So you can see why the variance, again, we've covered these before. So those are the standard deviations of position and momentum, and these are expectation values, and you've done those a zillion times. And remember that the uncertainty principle says that the product of the two unknowables is greater than or equal to a constant. And so there you go. So the important thing is of course, if one goes up, the other goes down. And so that's all fine and good. That's, these would be the fodder for early questions because it's incredibly simple, right? If one goes up, the other goes down. Those early questions, and again, you've seen this on the last test, they were stupid simple. They were stupid simple. They were like middle school level. I do that to help build up points, right? So you get some momentum going on the test. You're not going to pass with those early questions anyway, so I have no reason not to give you very simple early questions. Now, what gets a little bit more difficult is remember that the product of the two standard deviations or variances, I never keep this quite straight. It doesn't matter for the test. It's related to the commutator. And I know this was on the last test, but again, it does find its way to this test as well. And again, you can think of it as the difference in the permutation of x and p and p and x. Again, this was directly on the last test. But what I want to point out is, where did this h bar over 2 come from? It comes from, how do you know, these are operators. How is that equal to h bar over 2? How is that possible, right? And the answer was that we had to do an evaluation like this. We took the operators and we had them act on a wave function, and then we divided out that wave function at the end. And that's how we could figure out what a numerical value is for those operators. Okay, now the reason that's important, and I even said this at the time, is that this is also, operator x on a wave function, then divide out the wave function. That's how separability works. Separability is a very, very big part of this exam. It's just the thing I decided to ask questions on. Heads up on that. You know what? Let me go ahead and finish up some discussion of the uncertainty principle, and then I'll get into discussing separability. So separability is a huge part of the test. Give me a minute and I'm going to talk about that. But let me just finish up the bit with the uncertainty principle, and then I'll do separability next. And I am going to be talking about things that are on the test. Okay, so this was still, on the edge of the first test, on the right edge of the first test, and on the left edge of the second test is what the uncertainty principle does. So, and I harp on this quite a bit because it's so frequently true that, you've heard probably when you were in high school, you can't know where something is and how fast it's going. Almost everyone's heard that before, and oh, okay, well, isn't that weird, right? Sure. And that's what this stuff does. But my point to you, as you're almost like grad students, is that that actually does things. Now, I showed you a little video on quantum dots. Don't worry about that. That's not on the test. But it does things, right? And in the case, so let's have a trap. Let's just build a trap and put two wave functions in it. We got a real wide one. And then we got a real narrow one. And I guess if they're normalized, the narrow one is going to be like way taller, but anyway. Okay, now I'll call that A and B. Now remember what I was saying was that, a lower level understanding is that A, I'm going to use some like overly simple terminology and expressions here, but I think you get it. A is, so I should say it has high uncertainty in position, so therefore it has low, sorry my handwriting's bad, low uncertainty in momentum, right? Now B has low uncertainty in position. I mean, it's right there. It's like, it's, between 0 and like 0.1 and minus 0.1, 0.1 L, I guess. I guess it goes from 0 to L. What did I do that? It's L2. I hadn't thought of this at a time. So, yeah, I mean, I can see that the quantum particle B is right in the middle of the trap, and it looks like it strays no more than, say, like 10% right or left. So that means I have a really good idea of where it is. That means a low uncertainty in position, and therefore a high uncertainty in momentum. Now, again, the part where you gain a more higher level, senior college level of understanding is to understand the implications of that. So, therefore, A is higher energy than B. And for multiple reasons. Now, let me also state that that's kinetic energy, because inside of this trap, this is a weird. It's actually a free wave problem, right? It's a free wave because the potential is flat. It's just different than the free wave because the wave function has to end left of 0 and right of L. That's where the free wave doesn't. So that's why there's a difference. So these are technically like funny free wave problems. And that means that what energy it has is pure kinetic. There's no potential, at least inside the box, but you're not allowed outside the box. So the kinetic energy of A is higher than B. And there was a couple ways to think about that. One was, if you have a high uncertainty in speed, and that's B's case, then practically you have to be going quickly. Now remember I said, think of a car that's going like 1 mile an hour down the highway. Aside from getting arrested and all that, because that's weird, how much can they be varying, right? Sometimes they speed up to 2 miles an hour, maybe they stop. If you're not going fast, you just don't have a lot of wiggle room. Now, if you're going 100 miles an hour, the first case, that was low uncertainty momentum, that was B, all right? So that is a slow-moving vehicle, that has low kinetic energy. I hope I didn't screw that up a minute ago. Okay, so high uncertainty in position, low uncertainty momentum. Low uncertainty momentum means that you're not moving fast because you don't have, again, if you're going 1 mile an hour, what could your variance be? It's not going to be that wide. Okay, now, with the low, you know where the particle is, but you don't know how fast it's going, that practically means you have to be going like 100 miles an hour, because then your variation might be between like 150 and 50, right? So you can, it's just kind of sensible. If you're going 100 miles an hour and you're speeding up and speeding down for whatever reason, those swings in speed are going to be probably kind of bombastically large, like 150 to 50. So that spread is quite wide. So this guy had a spread of like maybe 2 miles an hour, and this one has a spread of like 100 miles an hour. All right, so that was just one way to understand it. The other way to understand it was visually, which was let's take the narrow case, and this is B. And remember I said that this is composed of momentum waves, e to the ikx waves, and I showed you a nice little computer graphic, which was not, obviously this is drawn by hand, because you see me doing it, but that computer graphic was not drawn by hand. It was perfect. I seriously took this thing apart and I decomposed it into those little waves. And the purpose of that was to show you that I am able to sum up a certain number of waves, and it does equal the starting wave function. And in the case of a narrow one, I really had to do a lot. And I've lost how many wiggles I'm supposed to add. Okay, and of course the wide one, The wide one, case A, only needed 3 of them in the case that I gave. Now, the point of that was that if like in the case of B, if I have to add a wave, I have to add a higher energy wave, right? Because you see why? That's the lowest energy momentum wave that exists. So if I have to add more, and that handout shows you I have to add more, the only thing to be added has higher energy. And you had a homework question where you saw how no matter how you slice it, if you're going to add more waves, now the weight of the sum of the weights of each wave has to add up to 1, so you have a constraint in that regard, but that actually doesn't affect the outcome. The more higher energy waves you add, the higher the total energy compared to this one. So that was another way to see that. All right, now this came out visually, by the way, and hopefully I'll find the video and you'll see this here. But you recall when I just wanted to kind of motivate you a bit, and I knew how to make those little animations of those waves hitting those barriers. And remember how I said that at the beginning I drew a wave, and I drew it like a particle in a box wave, and it was on a track to hit the wall. And over time it actually got way wider, right before it hit the wall. And I had to actually scale the figure over time because of that. Because as it got wider, it actually shrank a lot. So I actually had to scale the y-axis. That's why it may have looked a little weird. Now, why is it getting wider? Well, it's because this is composed of a whole bunch of waves. Now, I made them all out of right-moving waves, e to the ikx waves, but a bunch of them. So some of them were going very slowly. So those are like here. And then some of them had been going very quickly. They were the high energy waves. And those traveled quickly, and so those were kind of out here. And again, there's a bunch of them, and that's why you see still kind of like a bell-shaped curve. But that's why it got wider. This guy has a bunch of waves. Once you hit go, some of them move quickly and some of them move slowly. So there was a dispersion to make it a little bit wider and wider as time went on. So anyway, that was just another manifestation of that. Okay, now, what do I want to do next? Tell you what, let me continue on. I said I was going to cover separability, but tell you what, let me do flat waves a little bit more because I just started talking about that. Again, I cannot dramatically emphasize, I put a lot of separability questions on the test, but you know what, since I started talking about this, let me continue with this and tell you, I actually do have a lot of step potential. I have a lot of these problems on here, so let me tell you what I did with that. And, well, let me remind you what this stuff is. Okay, so once we got to step potentials, and let me get a big pen to it. There's this thing's about to die. Let's see. What do I want to say about step potentials? Okay. All right. Let me start with the simplest step potential that we had, the one I just drew, and of course it goes on forever. And these are all flat. So I always found this funny. The free wave and the step potential, they're all, even particle in a box, they're all technically flat potentials. So the fact that there's like a discontinuity, and of course that's at like x equals 0, that does not count. It's still a flat potential, but it's not. That kind of bothers me. Anyway, okay, so of course the Schrodinger equation, minus h bar squared. And remember m is mass. I should write that out anyway. You know that we now have two m's. M for the quantum number for 2D rotation. That certainly is unfortunate. So the potential energy operator is just a number. Of course, the wave function multiplies it equal to the energy. So here's our eigenvalue equation. And the potential, it can be 0 or it could be an EV, it can be a number. 0 is also a number. If it's 0, of course, it's just the free wave problem, but that's not on the test. Let's see, but now, regardless of whether this is a constant or not, the solution is always ae to the I kx, right wave and left wave. So it's always that. And let's see. What else can I say? Remember that, unfortunately, we do get into these little details, but unfortunately it is important, so we do have to deal with this. So just do your best with this. In which case, you have to worry about when you're in the potential that isn't zero, you run into a problem with the k's, right? So assuming, so if V naught is greater than 0, then you can have two things happen. Sorry, actually, let me do if V is equal to 0, then K, let's call that K1, because that's how it usually came out in our different models. That was quite simple, 2me over h bar squared. Okay, but if the potential was not 0, we ran into this problem of you have to know whether the energy is greater than or less than the potential. So it's like if, right? I have a bunch of if ands. Programmers probably do well in this class because they're used to that stuff. So in this case, let's call that K2. So this would be like that's region 1 and that's region 2. So in region 2, we could have one of two situations, 2m e minus v over h bar squared. And really, these are the same equation. It's just that if e is less than v, I'm tempted to do this. All right, if e is less than v, then that's a negative number. So what I want to do is factor that out. 2m, then I've got v minus, sorry, that's a little v naught, right? V naught minus e over h bar squared. And then I'm going to take that minus sign out and put it out as the letter I, right? The square root of the negative is the letter I. Okay, so these are really the same thing, but we choose this one when energy is greater than the potential, and we choose this one when energy is less than the potential. So that was a little bit of a nuance, but it does have the benefit of actually being the same equation. You just saw how I can work through that, right? So it's not too bad. Let's see. Then we also have to remember certain things like what is the purpose of this, right? This is the infinite step potential. Why am I trying to work on this? And what could it describe that might be useful? Well, seeing how I've got left and right waves, let's say that I've got A waves are always like right waves and B waves are moving to the left. So what I might have here is an A wave that comes in, it hits, reflects, it's coming in, but then a B wave reflects back. If the energy is too low, it'll do this. If energy is less than V, if it's greater than, it'll move on. And either way, and of course that would be a right wave, that would be a C wave. What I can get from this is a definition of the percent reflectivity, which would be the weight of the wave function that's reflected divided by the weight of the wave function that is oncoming. So that was just something that you can calculate with this. In fact, given the nature of it's just a step potential, I don't know what else you could calculate from this, right? I mean, what else is there? I mean, it's not going to tell you the answer to your life, right? It's just this. Reflection, of course, transmission is 1 minus that. But what it does do, though, is it does show one thing, and let's graph it. So that's the y-axis, and here is the energy over the potential energy. And what you would expect is the reflection, if the energy is too low, it should reflect to 100%. Remember, 1 means 100%. And oops, not 0. When the energy, and that's true, it will reflect to 100%. Now, when the energy is greater than the potential of the energy of the oncoming wave is greater than the potential energy, it ought to just, the reflection ought to go to just 0 immediately, because again, if the bird flies higher than the wall, it goes over the wall every time. But you learned that not a quantum mechanical bird, it actually does this. So what you get out of this is very quantum mechanical behavior. While if I normally throw an object over the wall, it goes over the wall every time. But that is my observation of working with non-quantum mechanical objects. If I can shrink myself and throw an electron, it might not. It probably will, but it may not. And the only way to make sure is if I really give it a lot of energy, way more than the potential. So if I throw it like twice as high as the wall, it'll get over then. But still, even now and then it won't. So that's like completely like that. That is so strange from everything that people knew up until the 1920s, which is Newton's equations of if I throw a ball over a wall. That's all they knew at the time. So this was really, really nutty stuff. Sorry, the camera ran out of memory. Never seen that happen before. Anyway, so I hopefully fixed it, and we're back in business. Okay, so next bit, of course, is one thing I know that has in classes before that got lost that people didn't seem to follow was that when you're looking at these types of problems, we hit a barrier problem, and I know that I probably didn't help by talking about region 1 and region 2. But really, these are all one wave function. It's just one wave function. It's not 2 left and right. It's one wave function, and it has one energy. So I've had some people, like if I ask a descriptive question, I've had some people lose points by saying, well, the energy over here is this, and the energy over there is that. There's only one energy because it's only one wave function. It's only one particle. In fact, look at, if you're talking about this, like region 1, where this is the momentum, here's E, it's the same energy as in region 2. It's the same energy, it's the same particle, it's the same wave function. Now they have different kinetic energies, and that manifests in different momentum, but the same total energy. Now regardless, when you're trying to do whatever it is you're trying to do with these things, you always have to make certain that the wave function, because it is just one wave function, it always has to be smooth and continuous. Like when we first talked about how a wave function can't have any sharp edges no matter what, no matter where. And to make sure of that, when we have these types of steps, we have to make sure that they're smooth and continuous, and that allows us then to figure out, like, is EVA, A plus B, is that actually a sine wave, or is that a cosine wave? And then it allows us to determine what the K's are, and once we know that, of course, we know what the energies are. So smooth and continuous is often how we have to solve these. And I do have a question like that on the exam. Often it comes down to what we call like a log, I call it a log boundary. A log boundary condition. And, like natural log, the derivative over the function itself, right? That's like the change of a natural log. So remember that little dash means derivative. I hope you remember that. In one region at x equals barrier. So let's just say that's x equals, no, I'll just say barrier. Over the wave function, it's got to be equal to that's like the left side. That's got to be equal to the right side. And of course just the same wave function. Sorry. Barrier, so it's a little shorthand. Okay, so this little handy dandy formula, recall that it actually has every effect in it at once. You've got the smooth, the derivatives have to be equal, and that's what makes something smooth, but the points have to touch, which is continuous, and that's on the bottom. And it just turns out that it doesn't matter if you can flip this over, by the way, it wouldn't matter, you'd still be able to solve it. It's just that in all the model problems we have, it's always faster. You always find that however you work it, that this approach is always the fastest. So that's why I tend to show it this way. So, so again, this is how you figure out what things are. Let me give you an example of how boundary conditions affect answers, right? So the free wave, there's no boundary condition, so there's no quantized energies. A and B can be anything. It's literally a free wave. It's literally free for all. It can do whatever it wants. It can move left, right. Okay, now on your last homework, maybe it's your present homework. I don't remember. Maybe I'm about to give a whole bunch of answers on your homework. Actually, I have no idea. I'm just going to tell you anyway. All right, so you're going to have to give me some internet points for that, all right? Okay, so let's take the free wave and let's add a boundary condition. Right, let's make the potential infinite at 0. Now, what you get from that is that, again, if you were, in this case, you have to have the wave function. The wave function has to be 0. The wave function at x equals 0 has to be equal to 0. And what you find is that a is equal to minus b, and therefore the wave function is a sine wave, sine kx. Okay, so on and on and on. Okay, but there's no other boundary condition, right? I didn't put another wall up, which would then be a particle in the box. On your homework problem, right, I didn't have any boundary. There's just the one that means that your wave function is a sine function, but then there's nothing else. Now that means that there's no wave function that then makes the k have to be something. The k is energy, and therefore there's no quantized energy levels. The energy levels can be anything. So anyway, I'm just trying to give you an idea about how boundary conditions work. So this example isn't quite the same as that because there's not really two regions. But of course I can make two regions. Let's just say that there is a wall right here at x equals L. All right, and that goes off to infinity. Now you see, now you got yourself a second boundary condition. And when you do that one, then k cannot just be anything. K has to be, it actually has to be like a integer times pi over L. And that way the sine function starts at 0 and ends at 0. And that is, the left side is because it's a sine function, and the right side is because k is some integer times pi over L. So that's how boundary conditions work, right? The problem will explicitly set up a boundary condition. The boundary conditions do whatever it's going to do. It may do a lot, like particle in a box, where it quantizes the energy levels and says you were working with sine functions. Or in that example on the homework, it may not do anything. It may just say that there's just a sine wave. And of course, if I didn't have any barrier at all, then it's a free wave and there's no boundary conditions at all. Okay. Step potentials like this require these log boundary conditions. And then don't forget that we also had, here I'll put it right here. We also had the finite barrier. The finite barrier also does make it to this test. And it's, as some of you, I'm guessing some of you may have looked at that handout I prepared. Oh, remember I had a fun little video of it, right? And I hope that was interesting. It took me a while to make it, but anyway, I just hope that the finite barrier isn't such this abstract, like what the heck are these waves doing? What does it mean to reflect or transmit? So I hope that video kind of made that more clear. But when you solve this, you don't solve this for a little, like a little wave state like that. That's what I did in the video. When we actually do the solution, we're actually using, A and B waves, and then you have a C and a D wave, and then the wave that goes out to the right is purely transmitted, so that's just an e to the ikx wave, so that's just an E wave. Recall that in this region, you're going to have a certain momentum of K1, which will be just like I've created over here. There's no potential energy. Recall in the transmitted area, that has the same momentum. It has the same momentum because it's all one wave function, and it all has the same energy. Now, in regions 1 and 3, you're going to have the same kinetic energy because there's no potential energy on either side. Region 2 will have less kinetic energy because it has potential energy. Now, the way that manifests itself is that the wave will look something like this. So it'll be kind of wiggly. And then, of course, maybe the energy is kind of low. Now, if it passes through, the frequency of the wiggles is the same, it's just there's less amplitude, right? See, I didn't draw the wave as tall. I tried to draw them just as wiggly, but not as tall. So the transmission was not 100%, so that's what that means. Now, also recall that if, I remember showing the graph in, that's one of the ones I did with the computer. I showed the percent transmission as a function, again, of energy over potential energy. And here's 1, here's 0. And recall that this is where quantum really does some things, right? And the way the graph looked, let me just show you what the graph looked like. Look like that. And of course this is 1, so that's 100%. Here, I'll make that a little bit more clear. Okay, so this is all kinds of messed up. So again, this is, if you do that crazy analysis, again, look at the handout. If you really want to kill yourself, look at the 20 pages of algebra I did. But this is the end result. And you see all kinds of crazy behavior. The particle can transmit through, it can tunnel through, even if it doesn't have enough energy. So that's all like right here. That's really bizarre. So you've heard of people saying, oh, quantum mechanics says you can walk through a wall. Actually, yeah, I mean, it does. It's right here. It just says it's improbable, so that's why you shouldn't try it. Where it gets really strange, though, is that if you have more than enough energy, you can just transmit right through the barrier. That makes sense. But as you gain energy, all of a sudden, that becomes less certain until you pick up some more, and then you'll transmit through the barrier, 100%. But then it goes down again, and then it goes back. What? I mean, that's crazy. Yet we see that behavior all the time. There have been experiments that have tested this, and it's like perfect. It doesn't make sense, but things do this. Now recall that one thing I tried to do in that little movie I showed was to show you that I could change the barrier. I think I had a barrier that was 10 times bigger, and yet more of the wave actually still got through it. And that's just that's just weird behavior, like I'm trying to show here. And if you're thinking like, well, how do I know, if I have an electron and the barrier is 10 times bigger, how do I know whether it necessarily goes through better or not? The answer is you have to solve all this stuff, right? So it's good that we know how to do this. But if you practically, if you're working at Intel and you're trying to design a new computer chip, and for some reason you need to know this, which is not that fanciful, I mean, that's literally what they do there, then you have to have the mathematical chops to solve it. And you may be thinking, oh, that's not me, that's not poor you, by the way. Rich you will figure it out. So which one are you? You decide. So, let's see, now what I want to talk about. I guess, let's see, let me just do a little bit about vibration, and then we're going to get into 2D rigid rotor, and then I will start mentioning separability, which is terribly important. I'm out of room, so let me wipe out the board, and we're going to do vibration, and then we're going to do separability. All right, so vibration. Vibration was the last of our there's just like one-dimensional, then we got into multi-dimensional stuff after that. Okay, when it comes to vibration, this is really tough. Every year that I have to write homework and exam questions, it's tough because there's really not much to work with. Think about like when I solved the energy of the ground state, that took about 20 minutes and it got kind of ugly. I was running out of room. That's not, I'm not going to ask something like that on a test, even COVID or not. I wouldn't have put that on a test because it's a little too much. So I do still have questions on the exam about vibration. But I'm just telling you, it's not going to be something like that because that's just a little bit, it's too much. So what do I have? Well, I mean, I know what I have, but let me just tell you that all it comes down to is just knowing that you have this potential energy and it's parabolic. So I'm just going to draw. I'm going to just literally draw everything. So it's parabolic. There's some 0 point energy, and I'll represent that with a line that's slightly above 0. 0 on the potential. Notice that I put 0 right here. Remember, that's the displacement of the bond distance. It's not the bond distance. The bond distance is not 0. That doesn't make sense. This represents the displacement. So to the right is a stretch, to the left is a compression. And let's see, so with the potential energy, which is 1/2 k, the spring constant, x squared, so it's parabolic potential energy. Let's see here, so I'll have to draw this a little further out. The ground state wave function looks like that. It's e to the minus x squared looking function, which is a Gaussian or a bell-shaped curve. Oh, that doesn't look so good. I was doing so good, right, wasn't I? It's like I was drawing a really nice parabola, and I kind of blew it on that. Oh, anyway. Okay, so there's that one. Then, let's see, a unit of energy higher is the first excited state. And recall that these actually really look a lot like particle in a box. It always kind of bothered me how much they look like particle in a box, but they don't end right at the walls, right? So let's see, the first excited state has a node, so it means it has more kinetic energy. It actually, I didn't have you do this on any homework. I don't know if I said it in class, but it actually stretches a little bit further out. So it experiences a little bit more potential energy, so it has more kinetic and potential. But of course it does. It's an excited state. It has to have more energy. And it has more potential and kinetic energy. And again, kinetic energy is due to the curvature, which having a node increases the curvature. Remember, curvature is the double derivative. The kinetic energy operator is the double derivative. And it spreads its wings out further, left and right, so it has higher potential energy. So, I don't know, there's much. What else have I got? Let's see. The wave functions, of course, are normalizations. Depends on the quantum number. And so, yeah, these are bell curves. And alpha is a function of I don't even remember what it is. It's square root of something, something. I think there's an h bar in it. Anyway, it's a function of the mass and the spring constant and whatnot. Recall that this is the Hermite polynomial. It just basically introduced nodes, and normalization is normalization. We're starting to see how we're seeing quantum numbers come up more and more, where, let's see, so we have the quantum number plus 1/2, h bar is h, and the frequency, the angular frequency of vibration, which is the square root of the spring constant over the mass. Obviously I don't care about that. This ni is a quantum number, 0, 1, 0 for the ground state, 2. And again, you can see how there's a 0 point energy, because even if the quantum number is 0, the energy is not 0. The last thing we talked about were turning points. Oh God, where's my notes here? We talked about turning points, which I'm trying to kind of crudely represent as the point where, where the potential is equal to the total energy, and that means that if you stretch further to the right, so that would be, if you stretch further to the right, there's so there's 8% of the wave function is to the right of the turning point. And again, it's another one of those quantum mechanical things. It's like tunneling through a barrier when you don't have enough energy. This is the bond stretching such that it has negative kinetic energy. The potential energy is greater than the total energy. And that means the kinetic energy is negative. How does something move with negative kinetic energy, with a negative net velocity? I don't know. No one knows. It doesn't make any sense. It doesn't make any sense at all, but there you go. So that's just another interesting aspect of this stuff. I also tried to hopefully make it relevant to stuff. I know most people go to grad school in organic chemistry, so I always get a couple of folks will go to grad school. So, so if I try to draw like a parabolic bond, like right here, let's say that I have an organic molecule, and it's composed of CH and CH and CD. Well, sorry, hold on, let me. Yeah, so there we go. So let's look at a real potential energy surface, which can be much more complicated. So here's our parabola. But we all know that a parabolic, I mentioned this in class, the parabolic potential energy surface is really unrealistic. This is just not correct. Really, you can't compress things very far without the energy just going way up. And if you go too far, the bond will break. So now, in an organic molecule, which has CH bonds, if you think the CH bond is breaking in the process of an organic transformation, which may be like really important for making chemo, or maybe it's for a fuel of some kind, we'd like to know mechanisms, because mechanisms allow us to manipulate and expand and make it more efficient, but we need to know the mechanisms. And so if a CH bond is a part of some kind of process, and so there's a certain amount of energy that is required to break to get over that barrier, then what you do is you replace it with a CD bond and it will take more energy because of that different 0-point energy. And so that's one thing that's actually kind of important when it comes to quantum, vibrational quantum mechanics, and this is something we see happen all the time, so that's like one area that it's useful. And that's really all I've got to say about vibration. I do have other ways of incorporating it, and I think I put this on your homework. Let's go now, after we did this, we went to multidimensional, and we went from 1D to 2D, and I'll get to separability in a second. I've been talking about it incessantly. Some of the important things are, of course, it's on your homework, and I've said it a zillion times. Let's do like a double particle in a box, right? So here's our particle in X, and the boundaries, of course, are 0 to L. If you go outside of the boundary, then you have infinite potential energy, and this is X. So what I do is I will draw now in the Y direction, and that's also going to go from 0 to L in the Y direction. And I'll try to make this as 3D looking as I can. There you go, it's dashed because you can't really see it, right? Okay, so I've added the same thing in the Y direction, and I've made it just as long. And well, I didn't have to. I can make this one Lx and Ly. The wave functions are going to be just the multiple of sine nx pi over Lx times sine, painting myself in the corner here. You'll have separate quantum numbers for the x and y direction. Okay, so those two multiply, and the energy will be, you can plug that to, the Schrodinger equation. That's what it does, and get the energy. And what was, and so the energy set, so it's kind of interesting, and you did this on your homework, the wave functions multiply, but the energies add. But it'd be strange for energies to multiply, right? Oh, that's Ly squared. I think it's like everything is squared, isn't it? Okay, so there's that. I also want to point out that you had the potential for degeneracies. This is where I introduced degeneracies. You only get a degeneracy in this case if Lx and Ly, they would have to be the same. Now, of course, the mass is the same because it's the same particle. But if Lx and Ly are the same, then you can have degeneracies, because if you have a quantum number of, say, 2 for x and 1 for y, then you can have a quantum number of 2 for y and 1 for x, and those are the same energy. So that means you have two states with the same energy. And that may be like, oh, whatever. But it became terribly important, it will be terribly important when we get to the hydrogen atom and we have p orbitals, right? So you have only a single s orbitals, but when it comes to p orbitals, you've got px, py, and pz. Those are three degeneracies, three states with the same energy. When we get to d orbitals, there's 5 of them that are degenerate. dx squared, dz squared, x squared minus y squared, dxz, yz, and xy. I think those are the 5 d orbitals. So degeneracies are actually terribly important, and this is the first time you've seen one. And let's see, there's other tricks I can play. Now you saw that. Okay, again, I'm pretty sure I'm talking about the present homework, so I might be giving some answers, but oh well. The thing I like to play games with is, and I did this on your test, is that I didn't have to make one of these a box and the other a box. I don't have to do that. I could make one of them a parabola. So let me change that. I can make y. Here, I'll have to redraw. Here, let me just redraw this. So I can make the x dimension a parabola, but then I can make the y dimension, here's y, I can make that just a box. And so anyway, that would go on forever. And that looks like that, right? Did I do a good job with that? I did okay. Anyway. And what that would manifest itself as, it's all right. The wave function would still be separable, and so I'm about to get into separability. And what you would have is some normalization constant. I'm not too worried about that. You would have a regular wave function, let's say ground state wave function, for vibration in the x direction, and then you would have a regular particle in the box wave function in the y direction, and then you would have the energies, would be a mixture of the two. You would have a vibrational energy in the x direction added to the particle in the box energy in the y direction. So there you go. So this is something I play games with, right? Because you can see how I can just kind of mix these together. And so look out for that, because that's like the only thing I can do with like vibrational energy is just to do stuff like that. Okay, next bit is we got into rotation. And okay, so you on Monday's lecture, assuming, so I should have this posted Tuesday, and I'm assuming that you watched Monday's lecture. A mistake a lot of you made was a lot of you did not watch the last lecture before the exam. Now, I know the last lecture was on 3D rotation, but I didn't put too much of it on the test. But you're going to miss at least 2 questions if you don't watch Monday's lecture. So as we go into greater multi-dimensional this and that, x and y and z, multi-dimensional, I can do these particle in the box things, but I mean, that's it. I mean, I'm done. There's really nothing else you can do with this. There's not any tricks or interesting problems. What we do is we go to our cylindrical coordinates, or we go, as you are just now seeing, to full spherical. And of course, what we do with that is to cover rotational quantum mechanics. I gave you that, I know it's not great, but it's the best I could do, that little textbook I'm writing. And so you have that, so those are basically my notes transcribed. And it's important because atoms are round. And this is where you're going to see why do we have px, py, and pz orbitals. It actually is the spherical, it's the rotational part that does that. So it's kind of terribly important. The first problem we run into is that the kinetic energy operator is still this. Plus y plus z. But now I've got to have it in R. here, I'll just do this for 2 dimensions, like I did in class. You know, I just want to do this, right? I just want to, oh, okay, well, let's just make that R and phi. And of course, the answer is that that is absolutely wrong. That is not how you do the transformation. I mean, it looks nice and simple seems like, you know, isn't the simple answer always the right one? But no, not when it comes to mathematics. The answer is, God, I forget this. What is this? The product rule. So let's figure out how to transform x. And this is on the test, by the way. The way you do that is, I have the formula on the cheat sheet, so you know it's on the test. But, you know, it's kind of good if you can kind of just figure things out without looking on the cheat sheet. It's still there, but if you can just do it off the top of your head, then that's great. So let me do R. Now, I always remember that I'm trying to end with the change in R. Okay, but then, you know, the change in x still has to be the change in x. That means my change in x needs to be here, and so to cancel out the change in R on bottom, I'm going to put the change in R on top. There you go. So the way I can double check that is I can just cross these out, and change in x is change in x. All right, so that's how I know I did it right. Okay, so what do you do next? What is the formula for R is, of course, the square root of x squared plus y squared. Now, this thing, you don't do anything with this. This thing is fine, but you have to manipulate this one. And it ends up being, oh my God, 1/2 square root of, that's 2x, right? X squared plus y squared. I'm just doing this off the top of my head. Okay, so the 2's cancel, and what you end up with is x over r, ddr, okay. And if you stop there, you got it wrong. All right, you see what I did? The problem is that I'm trying to go to r, theta, and phi, and I've got an x there, right? And so that's not an r and a phi. So what you have to remember that x is actually r cos or sine. I don't quite remember, but anyway, so that's how you do it. Now, of course, you would also need to add in. Let me just wipe this out. You need to also add in the other. There's 2 things, right? An r and a phi. I'm doing the 2D case. Okay. And of course, if there's a theta, then you add that term. And hopefully, you know, I showed you enough to get you started, to get you an idea. But I also mentioned that if you have a theta and then you do the double derivative, and then you do that with y and z, it's multiple pages of algebra. I've never even tried it myself because I find it to be just simply absurd. Okay, so when you work all this out, when you get the double derivative of x and y, what you find is that, and I even have a video where I show you how to do this. I used to have a homework question based on it, where the whole homework was just to do this transformation. But I stopped doing that because it was kind of absurd. Let's not forget our constants, right? That's a surefire way to blow it. What this transforms into is, of course, 2 times mass. Now, of course, we've made the radius is defined as being constant. And you're going to see when it comes to hydrogen that you can't do that. And so the Hamiltonian's even going to be a little bit worse. That's what happens the week after the test. So trust me, that's going to suck. The mass times r squared, that is actually a well-defined thing in physics. That is the moment of inertia. So let me just wipe that out. Minus h bar squared over 2 times the moment of inertia. There you go. Now, of course, what you would do with this is you need to multiply it by a wave function, and of course that the definition of quantum mechanics is that you set that equal to the energy times the wave function, and what wave function you find will do that is the right wave function. And then you can analyze it for other properties and whatnot. And what's nice about this is you may notice that this is the free wave problem. This is the free wave problem, but instead of an x, you have a phi. But I mean, what would that matter? So you would expect that the wave function, here's the normalization. I think that's right, but the normalization never actually really is important for any of the questions I ask. You may have noticed that normalization is important for expectation values, but really nothing else. Okay, so I've got e to the I m phi, so it's just like a free wave. M can, the other difference, it seems like a difference, is that free wave can be e to the ikx or e to the minus ikx. Actually, m can be negative, so there's your backward, right? So e to the ikx is moving forward, e to the plus m phi is like turning clockwise, and e to the minus ikx is going to the left, it's going backward. A minus m means that you're rotating counterclockwise. So the analogy is really quite straightforward. You have to think a little bit, but not terribly much. So this is very much, you're seeing a lot of, this is all like free wave. So as I was telling you, it has a lot to do with free wave, except m cannot, it can be positive or negative, but it can't be anything. A free wave k can be negative, positive, it can be anything. 0 for something not moving. M can be 0. The particle can choose not to rotate. It can be positive and negative, but they have to be integers. So that is where it's like a particle in a box, right? Because you see quantized energy levels. Let me write this down. Particle in the box. So a 2D rigid rotor is simultaneously a free wave, in that I've got e to the momentum, whatever, x, a phi instead of an x, like a free wave. But it has quantized energy levels, which is like a particle in the box. So it's like a combination of the two. And of course the energy ends up being h bar squared m squared. That's the angular momentum squared over 2 times the moment of inertia. So there's that. And with that, we then get into 3-dimensional this and that. And now I need to spend a lot of time on separability because actually I wrote that part first, and then I decided not to talk about it first, but this is really important. Okay, when it comes to 3D, again, I don't have too much on it. It is on there. I have a question on 3D rotational this and that is on there. There's not a heck of a lot I can do about it. Here, let me wipe out the board real quick. And let me just write out the Hamiltonian on that. And we can kind of look at it for a bit, but then we're going to talk about separability because I spent several questions on the exam are about separability. Okay, so of course we've got h bar squared over 2 times the mass, which I now write out because m is a quantum number for 2D rigid rotor. Again, r is constant, so that gets factored out. And now we need to worry about separability. Now, in case you forgot what that is, I'm going to talk excessively about that for about 10 minutes. But the reason it's important is that the Hamiltonian has got to have terms with only phi in it, and then terms with only theta in it. And now, again, you know where this kinetic energy operator comes from. It comes from doing that transformation I literally talked about 5 minutes ago. It does look kind of awful. Yes, that's true. The hydrogen atom will be worse, but this is what it is. Now, Schrodinger says if you have the Hamiltonian, you add a wave function to the right, and then when you do that, you're going to find that it's still equal to itself times the energy. Okay, so that's great. Where we blow separability is right here, because there's a theta, and there's a phi. And what ends up happening is you can actually just do a lot of algebra, including multiplying by sine squared, and you end up with terms with just theta, terms with just phi, and then terms with just theta. Where it gets really funky is that the energy ends up getting the theta term. It ends up getting a sine theta squared. So energy ends up funneling into the theta way of the theta mini Schrodinger equation. And so, again, I know we just touched on the subject in Monday's lecture, so I only have, I think, 1 or 2 questions on the exam about it, but watch that lecture. It should be fresh in your memory, so I don't want to say too much about this, because what I really want to talk about is separability. So I'm going to wipe out the board and spend the last, I know I'm way over time, but this is important because it's on the test. So I'm going to wipe out the board and then talk about separability, and then we're done. Okay, so separability really got important when it came to the 3-dimensional rigid rotor problem. It's going to be hugely important next week when we get into quantum mechanics of hydrogen. We only have 1 week of quantum mechanics. After next week we do hydrogen atom, and then we leave quantum mechanics. So that's nice, right? And we talked about separability. Actually, we talked about separability. It actually came up in the Planck distribution. I don't know if you remember that, but it also came up when I talked about particle in a box in X and Y, and then it definitely came up in the lecture on 3D rigid rotor. It's going to come up again when hydrogen atom. So it's pretty important. And I found when I was writing the exam, I just really kind of harped on that. I had several questions, at least 3 questions about separability. Okay, so it's, let me write that down, separability. And it's, for 2D or 3D. It's when you have multiple dimensions. Of course, that's when you start seeing possibility of having degeneracies. And I will just kind of keep it simple. Let's say that the whole point of this is that the wave function, we're going to have, like an X and a Y, right? If we're in 2D, a Y better be somewhere, or you're not in 2D. And so separability is all about saying that it's going to be like sine kx times sine ky. That is opposed to like sine x times y. That is what you do not get. Now, if you think about it, what's great about this is that it makes solving this way easier. And if you didn't have this, if it could have anything, instead of sine x times sine y, if it could be sine x times y or sine x plus y, the degree of function space that could be the answer is infinite. It'd be like impossible to solve this stuff. It already kind of is, I know, but okay, regardless. So the point is that the wave functions end up being 2 different functions that end up being multiplied, and you did that on a homework, why that is the case. To prove separability, remember this. All right, so you have your Hamiltonian, and maybe you've done a whole bunch of algebra on it because you kind of know you need to. And then you apply your wave function. And of course, let's assume that it's in the separable form. And then you're going to divide it out on the left side. Kind of important to do that. Right? Now, you've seen this several times. Like I say, it came up when we were talking about the uncertainty principle. So you've been seeing this, a bunch. Okay, so what about it? You set this up, and maybe there's some product rules and some algebra. Okay, whatever. But it's got to be in the form of a bunch of terms with only x in them, plus terms with only a y in them. Now they can be equal to something. Not to be funny, it's just, like a constant. Energy could be 0, often it's 0. So when we did 2-dimensional particle in a box, it was equal to energy. When you do these rigid rotor things, 3D rigid rotor, it was 0. When we do hydrogen atom, the something will be a 0, just heads up on that. So there you go. Now, remember that you're going to have like operators, everything will only have an x in it. And let me give you an example of what that would look like. So these terms would look like this. So here is our wave function divided out on the left, and then we'd have like a double derivative. So there's our kinetic energy operating on the thing. And then on the right would be something, here's our constants. 2m over h bar squared. And maybe that something is energy, and so the x guy gets its own portion of energy. And what I see here is that then I can do a little algebra. I can just bring the wave function over, and I can bring the constants over. And what I end up with is looks like a free wave. It's just kinetic energy is equal to kinetic energy operator times the wave function is equal to the energy times the wave function, which we've been dealing with for about 6 weeks now. What's different is that the eigenvalue is just not the total energy, it's just a portion of the total energy. And of course the solution is e to the ikx, or e to the minus ikx, or sine kx, or cosine kx. The point is that when you separate these terms, you can unpack them into many Schrodinger equations in their own right. So again, once you've done the separability process, what you find is that it's actually the form of a differential equation, i.e. Schrodinger equation. It's just miniaturized because it only has one variable. And then the same is on y. And then it can be more or less complicated. And when you do that, when you have these separated into the different terms, what the meaning is, what that means is that your assumption that the wave function is like this is correct, that the wave function is composed of two functions multiplied. You assume that, try it, and then you get these separate terms. You got that, then it's correct. It's correct to make this assumption. The other benefit is, again, that each one actually ends up being miniature differential equations in their own right, which are solvable, miniature Schrodinger equations which are solvable, and now you've got your answers. So, let's see, I just want to give an example of that, and now I'm lost in my notes. Anyway, so let's do the 3D. Let's do the 3D case and 3D rotational case that you just saw today. So I'm going to write out the total wave function. I'm going to keep it simple like that. And just like I said a second ago, here is the problem. That you've got a theta and a phi together, and that sucks. That is a major, major problem. And again, if you can't write these deals out as separate functions, then there's simply no way to solve it. So, you don't know if this thing is a function with theta times a function of phi. And if it's not, then I don't know what you're going to do. Okay, here's the constants, minus 2ie over h bar squared. Okay, so here is one that's problematic. So I'm going to end with this one. Here's one that's problematic. All right, the answer is that you're going to multiply. So this is just like your homework, right? You can see how I had a really simple one like this on your homework with x's and y's, and it's an analogy to this one. So that's like the number one on your present homework. So the way to get around this is you multiply by sine. You do that, and what do you get? You are going to get 1 over, now I'll expand these out as functions of phi and theta. So you get this, so there's a miniature Schrodinger equation, and then you're going to get sine squared over sine is sine. Sorry, my handwriting isn't great. I'm hopefully not making any mistakes. I'm actually doing this from memory, by the way. Now, okay, so the wave functions get canceled out. Remember that these are a bunch of constants. So that's all fine and good. Let's see, and here's where it gets funky, is that sine squared ends up being part of the energy. Okay, now, if you assume that that the 2D rigid rotor solution is still valid for that, then what you've got is, there's a miniature Schrodinger equation, and here is another mini Schrodinger equation. And what's funky about this one is that energy gets eaten up into it. So that's kind of interesting, is that energy ends up, unlike the 2D particle in the box, which x and y take a portion of energy, that does not happen in this case. In this case, the energy ends up funneling down preferentially into one of the miniature Schrodinger equations. So this ends up being like a dominant one. It ends up being like more important than this one. Not that this guy is unimportant. It's still a thing. In fact, what would this be? This would be minus m squared. So let me do some factoring with this, and let me tell you one last thing, a little deeper mathematics. You don't need to know this, so don't memorize this. So I'm just going to write this out, and usually we bring over the energy to the other side. And now, let's say that this is equal to minus m squared, so if I bring it over, then it's plus m squared. So there you go. And now you go look in your 18th century math textbook, and somebody solved this, and thank God for that, because I can't do it. I have no idea how you can go about doing it, but someone did. The last thing I wanted to say about it, right, so that gives you the energy, you get the wave functions, you get the energy, and that's all you want. Okay, anyway, I've talked way too long about that. Just for those of you who are mathematically inclined, I just want to show you a little bit more what's under the hood. I know I'm way over, but I did this to help you, so please, no complaints, all right? I'm trying to help, and not much else to say. I'll have extra office hours, so please sign up for that, and that's all I got, so good luck.